Welcome, everyone. Today, we're diving into a case-based question focused on polynomials, straight from Chapter 2 of the Class 10 CBSE syllabus. We'll explore how these problems work, step by step, so you can tackle them with confidence. Let's get started. Let's explore a case study based on a simple yet beautiful decoration, garlands shaped like parabolas on a door during Onam. We're asked to think about the quadratic polynomial that describes such a curve. First, what can we say about the sign of the coefficient in x squared plus bx plus c? Then, we'll find a quadratic polynomial given the sum and product of its zeros. Finally, we'll look at two options, either finding a value of k that makes -1 a 0 of a given polynomial, or calculating the sum of the reciprocals of the zeros of another polynomial. This blends real life with algebraic thinking. Let's explore the key points of this case study. We're looking at a water fountain shaped like a downward-facing parabola, with its height described by the equation p of x equals -x squared plus 5x minus 4. Our goal is to find where the water reaches its maximum height, that is, the value of at the peak. Then, we'll calculate that maximum height itself. Alternatively, we'll find the points along the x-axis where the water's height is exactly 2 meters. We also know each fountain rod stands 10 centimeters above the water level, which factors into our calculations. Let's look at a dolphin jumping out of the water at 20 centimeters per second. Its height above the water after some time t follows this quadratic formula, p of t equals 20t minus 16t squared. We'll use this to find a few things. First, where does the dolphin start and end its jump, the zeros of the polynomial? Then, what kind of graph does this equation make? Finally, we'll calculate the height at 1.5 seconds, or figure out the total vertical distance the dolphin covers before it hits the water again. Quadratic polynomials are powerful tools for modeling the curves and shapes we see in architecture. Take the Lusitania Bridge in Merida, Spain, for example. Designed by Santiago Calatrava and completed in 1991, this bridge gracefully spans the Guadiana River. Its name honors Merida's ancient Roman roots, when it was the capital of Lusitania. In this case study, we'll explore how quadratic equations relate to the bridge's arch, finding zeros, constructing polynomials, and working with sums and products of roots. Let's dive in. Let's take a look at Annie's dive from a 48-foot-high diving board. Her height above the water at any time t seconds is described by this polynomial. H of t equals -16t squared, plus 8t, plus k. Our first task is to find the value of k then. We want to figure out when she actually hits the water. Alternatively, we consider Rita's height, given by a different polynomial with zeros at 1 and 2, and find that polynomial. This case study helps us understand motion through quadratic equations. Thank you for joining me today. I hope you found this journey insightful and inspiring. If you want to keep the conversation going, you can find me at the handle on screen. Until next time, take care and keep learning.